Hello everyone in Chemistry 40S and Chemistry 40SH universe. This is Dr. Carroll here. If you didn't know that by now, it's Unit 6, Lecture 2. We're going to talk more about strong acids, strong bases, weak acids, and weak bases. So this is on page 15 in your booklet. So let's jump right into it. Remember, there's only 6 strong acids. All the other 1,000 acids that you may come across, 10,000 even, are going to be weak. So if you're going to memorize any acids, memorize the strong ones because there's only 6. And nitric acid is one of them, and that's used in this first example. We got 0.001 molar HNO3. We want to find everything, all we can about that. And to start that, we're going to write which I'm going to call an ionization equation. It may resemble the solubility equation from Unit 5 when we're talking about solubility and KSP and stuff like that. So what we have is we got HNO3, and then it breaks apart 100% to H plus and NO3 minus. So if you started with 0.001 molar of HNO3, you're going to get 0.001 molar of H plus and 0.001 molar of the nitrate. You don't use the nitrate for much after that, but it is just swimming around there. So to get the pH, it's -1 times the log of H plus, and you get 3. Because 0.001 is 10 to the minus 3, the log of 10 to the minus 3 is -3. Make sure you know how to do that on your calculator. -3 times -1 gives you 3, and that makes sense because we are talking about an acid, nitric acid, so the pH should be less than 7, and it is. The pOH is 14 minus 3, which is 11, and some of your students are going to say, well, with this equation, I don't see any hydroxide anywhere. But remember, all of the stuff that we're going to look at is an aqueous environment, so there's going to be some hydroxide in there. The H plus concentration is given 0.001. The nitrate is 0.001. The OH minus is 10 to the minus POH, 10 to the minus 11, or 1 by 10 to the minus 11. Percent ionization, all of it, 100%. Another way you could have gotten OH minus is just by KW over H plus. So 1 by 10 to the minus 14 divided by 0.001, and you get 1 by 10 to the minus 11 molar. And there's really not much more you can answer in that question. So let's jump to the next one on page 16. And here we're going to have example 2, HI, which is hydroiodic acid, ionization equation. HI goes to H plus plus I minus. You prepared a 0.026 molar HI solution, so at equilibrium you'll have 0.026 molar of H plus and 0.026 molar of I minus. The pH is -1 times the log of the H plus concentration, so -1 times the log of 0.026 is 1.59, and the pOH is 14 minus that, so that is 12.41. We got the H plus concentration, the OH minus, the I minus, they're going to be the same. The OH minus is 10 to the minus 12.41, which is 3.89 by 10 to the minus 13 molar. So let's see, pH is less than 7, that's good. It's an acid, that's good. OH minus is more than 10 to the minus 7, that's good. And a good way to check is multiply H plus times OH minus, because remember, H plus times OH minus always has to equal 1 by 10 to the minus 14, which it does. Example 3 is one where we bust the idea that pH has to be between 0 and 14. Here's a really concentrated hydrochloric acid solution, 10 molar. So you dissolve, it's a strong acid, so you get 10 molar H plus and 10 molar Cl minus. The pH is -1 times the log of 10. So log of 10 is 1, right? 10 raised to the first power gives you 10. So 1 times -1 is -1. So the pH is -1, which means the pH is 14 minus a minus, which is plus, is 15. The H plus is 10 molar, the I minus is 10 molar, the OH minus is 1 by 10 to the minus 15th. So that is allowed. There's the check, 10 times 10 to the minus 15 is 10 to the minus 14. Okay, now let's look at a strong base, calcium hydroxide. CaOH2. So we want to write the ionization equation and calculate everything we can about that. So CaOH2 goes to calcium 2 plus 2 OH minus. There's always some students who have problems with this because they'll write calcium 2 plus as 0.04 and they'll write the hydroxide as 0.04 as well. It's not 0.04, it's 2 times that. It's 0.08. So the pH is, well, I'm not going to get that first. I'm going to get the POH first because I got the hydroxide in there. So let's get the POH first. So minus 1 times the log of 0.08, which is 1.1. So then the pH is 14 minus 1.1, which is 12.90. That makes sense. It's a base. The pH should be more than 7. And then the H plus is 10 to the minus pH, 10 to the minus 12.9. So 1.26 by 10 to the minus 13 molar. And my calcium, that says calcium 2 plus, right? Calcium 2 plus aqueous at equilibrium is 0.04 molar, and the hydroxide is 0.08. I don't know what this is. Get rid of that. Okay, so that is example 4. Question? Send me an EDSB question. Page 16. On to page 17. Now we're going to branch from strong into weak. Okay, I don't know what that is. Get rid of that. Tropicana orange juice. You can choose the orange juice brand of your choice. I get no compensation from Tropicana for using that in this example. The pH is 3.46. We want to find everything else, the H plus, the OH minus, the POH. Now, in fact, as you might imagine, in something natural like orange juice, you're going to have more than one acid in there, right? You're going to have citric acid. You're also going to have ascorbic acid. Ascorbic acid is also known as vitamin C. So, and there's some other acids floating around there. Okay, so my H plus concentration is 10 to the minus pH. So 10 to the minus 3.46. I get 3.47 by 10 to the minus 4. So I know H plus, I know pH, so I know it's acidic. My POH is 14 minus my pH, 14 minus 3.46, which is 10.54. And then my hydroxide is 10 raised to the negative 10.54. So 2.88 by 10 to the minus 11 molar. And that's really about all we can do for that. Okay, so we went from strong acids. Example 5 bridges us into now a discussion about weak acids. A weak acid in general is given the symbol HA at equilibrium with H plus and A minus. Now I know I could do diprotic and triprotic, but all the examples we'll look at for weak acids will be monoprotic. So Ka is H plus times I minus over HA. It's a small number. We said typically 10 to the minus 30 to 10 to the minus 3. One thing, dissociation, let me spell that right. Percent dissociation is 100 times the concentration of HA that reacts over the original concentration of HA. So that is just like percent reaction 2 chapters ago when we were talking about equilibrium. We got percent dissociation. It's 100 times the concentration of HA that reacts over the original concentration of HA. And we're going to use these calculations. A little sidebar here is even though there's 6 strong acids and all the other ones are weak, you can rank the weak acids, right? Just like not every hockey team makes the playoffs, but the teams that don't make the playoffs are the weaker teams, but there's still stronger teams of the weaker set of teams, right? And that's what we're looking at here. I got HX, HY, and HZ. They're all weak acids, but HX is the strongest of the 3 weak ones because it has a larger value of Ka, which means, assuming the same original concentrations of HX, HY, and HZ, you're going to get a greater percent ionization of HX compared to HY compared to HZ because its Ka is larger, and these are values of Ka. Its Ka is larger, so you're going to have greater amounts of H pluses and A minuses relative to your original amounts. Well, okay, sorry, this is at equilibrium, but it's weak. It's not going to be that much different from the original amount. Okay, so let's look at some varieties of calculations associated with weak acids. The first kind, and I'm not going to label them as skill 1 or type A or type B. Let's just make little charts, tables, ice diagrams, things to help us to solve this. So here you're given Ka and you're given an original concentration. So we create a 0.1 molar acetic acid solution. We have the Ka. We want to find everything, the pH, the pOH, the H+, the OH-, the AC-, and the percent ionization. So all that stuff. So here we go. Start with an ionization equation, which I can write as IE, and somebody's going to say, no, you used that for ionization energy way back in chapter 1. Really? Some of you remember that? If you do, give yourself a standing ovation, okay? Even I didn't remember that, okay? I'm using IE for ionization. No, I'm not. Yeah, ionization equation. In this chapter, HAC goes to H+ plus AC-, IE is the ionization equation. Some books write this equilibrium arrow more dramatic, and they'll have the longer line pointed to the left to show that not much of the acid actually ionizes. Most books nowadays don't do that, but if you're reading some older books, and there's still some in the back of 308, okay, there's still a few left. You can pick them up in a few years if you'd like. Sorry, didn't say that. HAC goes to H+ plus AC-. So if I start with 0.1 molar of HAC, no H+, and no AC-, then what's going to happen at equilibrium? So let's say, let X be how much HAC is lost. So if I lose X of HAC, then I gain X of H+ and X of AC-. So it's a 1-to-1-to-1 ratio. So at equilibrium, I'm going to have 0.1 minus X of HAC, X of H+, and X of AC-. So that will be my equilibrium value. So I'm making an ice diagram, and I'm checking it twice. Okay, so then the Ka is X times X, H+ times AC- over 0.1 minus X. So it's X squared over 0.1 minus X, and it equals 1.8 by 10 to the minus 5. I want to solve for X. If I solve for X, then away I go and I get the pH and the pOH and all that other good stuff. The thing is, when I look at this, I say, whoa, if I cross multiply and everything, I'm going to do a quadratic equation. And you know what? I don't want to do a quadratic equation. We're going to be able to do an approximation that'll work in every example that we use in this course. The approximation is that the amount of acid that ionizes is going to be negligible, like insignificant, not very much, compared to what you started with. So what we do is, in the denominator of this equation, we just vanish out the X part. We can just think of it as being 0. It's way smaller than the 0.1. So my approximation is X is much less than, I put 2 less than symbols, much less than 0.1. So where 0.1 was the original HAC concentration. So therefore X vanishes, so I can now cross multiply. So X squared is 0.1 times 1.8 by 10 to the minus 5, which is 1.8 by 10 to the minus 6, and X is the square root of 1.8 by 10 to the minus 6. 1.34 by 10 to the minus 3. So notice I didn't lose all the 0.1. If it was a strong acid, I would, and the pH would be 1. But the pH turns out to be 2.87. Okay, more than 1, because it's not a strong acid, it's a weak acid. So my H+ is 1.34 by 10 to the minus 3. My AC- is also 1.34 by 10 to the minus 3. And my HAC is pretty darn close to 0.1, right? Okay, fine, 0.0987. I'm not going to use that number for anything useful from there. But so I got my H+ and my AC- are both 1.34 by 10 to the minus 3. My pH is 2.087. My pOH is 14 minus 2.87, which is 11.13. And my OH- is 10 to the minus 11.13, or 7.41 by 10 to the minus 12 molar. And it all makes sense. pH is less than 7. If I multiply OH- times H+, I get 10 to the minus 14. Okay, so that approximation helps a lot, and we're going to use it a lot. I can also get the percent ionization, ION with a little n with a line above it. This is shorthand for ionization. So it's 100 times how much of the HAC reacted. In other words, X. Some books will write it as 100 times X over the original concentration, and it's 1.34%, which is typical for a weak acid under everyday conditions. Okay, so that was page 17. Take a pause if you want for a minute. Have a glass of milk or something. Redo the questions. And we're back. Here we go. Example 2. Consider a 0.2 molar HA solution with a Ka of 2 by 10 to the minus 6th. We want to get the H plus, the A minus, the pH, the POH, and the OH minus, and the percent ionization. Might as well throw that in as well, percent ionization. So let X equal the concentration of HA that reacts. HA is my general form for a weak acid. HAC is acetic acid. H-benz is benzoic acid. HLIT is litmus, and we're going to talk about litmus a little later in this chapter. I'm going to get into titration curves and indicators. So HA goes to H plus plus A minus. You started with 0.2. H plus is 0. A minus is 0. So I'm going to lose X of HA. I'm going to gain X of H plus and X of A minus. So at equilibrium, I'm going to have 0.2 minus X of HA, X of H plus, and X of A minus. So my Ka is going to be X times X squared over 0.2 minus X. And we're going to get rid of the X in the denominator. So 2 by 10 to the minus 6 times 0.2 is X squared. X is the square root of 4 by 10 to the minus 7. 6.3 by 10 to the minus 4. So you see that here we just rounded the HA. We kept it essentially still 0.2. The H plus is 6.3 by 10 to the minus 4. The A minus is 6.3 by 10 to the minus 4. Now, if you're really wondering, does this approximation ever break down? The answer is yes, it does. If your original concentration, your 0.2, is pretty close than the Ka value, like within 100 times, then the approximation won't work. But this is a lot more. Ka is 2 by 10 to the minus 6, HA is 0.2, so it'll work fine. So let's just assume it's always going to work. Okay, so once I got the X, I know that the pH is minus 1 times the log of 6.3 by 10 to the minus 4, so it's 3.2. The POH is 14 minus 3.2, which is 10.8. And the OH minus is 10 to the minus 10.8, which is 1.6 by 10 to the minus 11 molar. The H plus, well, that's given, 6.3 by 10 to the minus 4. Those are 4s again. And the percent ionization is 100 times how much is reacting? 6.3 by 10 to the minus 4 over 0.2. And that's just 0.315%. Okay. Example 3 is one where you're using a solid and we have grams of the acid put in. So you take some pellets of benzoic acid, 1.22 grams worth of it, and we want to find everything, but we got to get the molarity first. The molar mass of benzoic acid you could calculate, C6H5COOH, is 122 grams per mole. So I take 1.22 grams divided by 122 grams per mole, so that gives me the moles, and then I divide by 0.2 liters, because 200 mils is 0.2 liters, and you're also given the Ka. So you want to find the pH, the POH, the H plus, the benz minus, the OH minus, and the percent ionization. Okay, you don't always have to find all of them, but you have to answer the question. Sometimes I ask you to find all of them. So let's start by getting the molarity. 1.22 divided by 122 is 0.01 divided by 0.2. 5 by 10 to minus 2 molar. So that is my initial concentration of benzoic acid. And I don't have any H plus or any benz minus to begin with. Now some students say, oh, but you always have H plus. It's always there in the water before you even spoon in any H benz. Yeah, but that is true, but it's a heck of a lot smaller than H benz. 5 by 10 to minus 2. So you can even invoke the common ion effect if you want to show that H plus originally is really insignificant compared to H bends. So we'll just start that as 0, and the bends minus is 0. There's some other, actually I should have said the common ion effect. That's coming later. So pretend I didn't say common ion effect. Good? Good. Because I don't want to replay this whole thing because I said that thing. So I retract the common ion effect comment. It is redacted from the transcripts. Okay, so if I let x be how much H bends is lost. This is a Saturday night I'm doing this, everyone, okay? So it's lots of fun tonight. So I lose x of H bends, I gain x of H plus, and x of bends minus. So at equilibrium, I have 5 by 10 to minus 2 minus x of H bends, x of H plus, x of bends minus. Put them in to my Ka expression. I got x squared over 5 by 10 to the minus 2 minus x is 8 by 10 to minus 6. Get rid of that x in the denominator. By the way, I'm not dividing x into x squared. Some students think somehow I'm doing that, or I'm canceling out an x, one of the x's. I'm not doing that. Relative to the original amount, 5 by 10 to minus 2, I lose x. It's negligible. It's like Bill Gates walking down the street and a nickel falls out of his pocket. He's not going to pick it up because he's got like $500 billion. It's negligible. Okay, so there you go. So do the math. Multiply 5 by 10 to minus 2 times Ka. Take the square root, and you get 6.3 by 10 to minus 4. So that allows us to get the pH, minus 1 times the log of 6.3 by 10 to minus 4. The bends minus is also 6.3 by 10 to minus 4. The POH is 14 minus 3.2. The OH minus is 10 to the minus 10.8, 1.6 by 10 to the minus 11. And the percent ionization is 100 times how much we lost, which was x, 6.3 by 10 to minus 4, over how much we started with, 5 by 10 to minus 2. And it's going to be 1.26%. Okay, so that's page 18. Now there's a second style of questions. Again, I don't want to label it as type A, type B. You can do that if you want, make up your own scales, but just to jazzy it up here, let's change the color, shall we? Okay, so here's example 1. Here you aren't going to be using the x's. You're given some initial and some equilibrium information, and you got to solve everything else. So there's no approximations involved here. Let's say you have a 0.2 molar HA solution, and they tell you, they meaning the question makers, is 9.86 by 10 to the minus 4 molar. We want to calculate all this other stuff. A minus, HA, Ka, pH, POH, percent ionization, and the hydroxide. Even though you're going to say hydroxide, I don't see any hydroxide in there. But remember, it's an aqueous system. So I start with 0.2 of HA, 0 H plus, and 0 A minus. At equilibrium, my H plus is 9.86 by 10 to the minus 4. So I gained 9.86 by 10 to the minus 4 of H plus, which is the same as the amount of A minus that I gained. So I had to lose 9.86 by 10 to the minus 4 of the HA. So at equilibrium, I have 9.86 by 10 to the minus 4 of H plus, 9.86 by 10 to the minus 4 of A minus, and 0.2 minus 9.86 by 10 to the minus 4, which is still pretty darn close to 0.2, but it's 0.199014 of HA. So my Ka is 9.86 by 10 to the minus 4 squared divided by HA. If you left it as 0.2, it'll be good enough. It's not going to make a significant difference. So I'm calculating the Ka. In questions we did before, I was given Ka. Here I calculated. And now I can also get the pH. So minus 1 times the log of the H plus concentration, 3.01, so that's good. The pH is less than 7. POH is 14 minus that, so 10.99. And the hydroxide ion concentration is 10 raised to the POH, negative POH, 10 raised to minus 10.99, 1.02 by 10 to minus 11 molar. So the percent ionization is 100 times how much reacted, 9.86 by 10 to minus 4, over what we started with, 0.2. So you get 0.493%. So that is the percent ionization. And that's about all we can do with that example. Let's look at the second one. We have a 0.7 molar weak acid solution. The pOH is given as 11.8. When I see that right away, I say, you know what, I'm going to get the pH. Did I do that in my head? Is it 3.2? No, that'll be 15. It's 2.2. 11 and 2 is 13. 0.8 and 0.2 is another one, so 14. I just wanted to get that right away because that's going to help me. I want to get everything else now. So HA, my ice diagram, I start with 0.7 molar. I don't have any H plus or A minus to begin with. And then, how do I get these equilibrium values? Well, I got the pH, right? 14 minus 11.8. So my H plus is 10 to the minus 2.2, 6.31 by 10 to the minus 3. Yeah, I can get the OH minus as well, 10 to the minus 11.8, 1.58 by 10 to the minus 12. But it's the H plus that I have to plug into my ice diagram. So it's 6.31 by 10 to the minus 3. So that goes in for my H plus. My A minus is also 6.31 by 10 to the minus 3, right? 1-to-1 ratio. So I lose 6.31 by 10 to the minus 3 moles per liter of HA, leaving 0.69369 HI molar at equilibrium. Plug those into Ka, and you get your value. You plug it into the Ka expression, you get a Ka of 5.74 by 10 to the minus 5. And the percent ionization is 100 times how much reacted, which is 6.31 by 10 to the minus 3, over what you started with, 0.7, and you get 0.9%. So that's the percent ionization for that weak acid. I don't know the identity of the weak acid, but now that I've done the measurements and got Ka, I could look at a table of Kas and maybe narrow it down to 2 or 3 acids. Okay, so now we're on to page 20, and it's getting late because I think things look upside down. So I'm going to go back up here to page 20, and I believe this one is going to involve where you're given the percent ionization, and you have to work from there. And as I'm going backwards here, I'm looking at some worksheets. There's lots of good practice that you can do with this question, these kinds of questions. I see common ion effect that I'm not going to look at. I see titrations. These are all some good things we're going to get to a little later. You may have heard of titrations in some cops and robbers TV shows, or your NCIS, or I think, is that what it's called? Law and Order, an order of fries with milkshake, something like that. Do you see how clever I was at just yammering away so you wouldn't say, how come Dr. Carroll had one page flipped relative to the other? And here we go. Wow, that was smooth. Was that not smooth? That might have been the smoothest thing you've seen today in your courses. So we have example 3, a 0.3 molar HA solution. Yeah, they tell you the percent ionization. So this one's a bit more exciting. It's 5.8%. We want to calculate the pH and the Ka. So how the heck are we going to do that? So my HA starts at 0.3. Now how do I get everything else? Okay, percent ionization is 5.8. So that equals 100 times how much I lost, which is x, over what I started with, 0.3. So if I solve for x, I'm in business. So I just cross multiply and end up with this. X is 0.3 times, I don't know, get rid of that stuff there. 0.3 times 5.8 over 100. So 0.0174. So that is my equilibrium concentration of X, because it's how much was lost, and it's all 1-to-1 ratio. So my H plus is 0.0174, my A minus is 0.0174, and my HA is 0.3 minus 0.0174, which is 0.2826. So Ka is 0.0174 squared over 0.2826, and I get 1.07 by 10 to the minus 3. So that is my value for Ka. And my pH is minus 1 times the log of 0.0174, which is 1.76. And I could get the pOH if I wanted to, right? pOH is, what would that be? 1412.24. 12 and 1 is 13. 76 and 24 is 14. And I could get the OH minus as well if I wanted to. OH minus is 10 to the minus 12.24. So I'm going to take a 12.24 negative inverse log 5.75 by 10 to the minus 13. Okay, so this one was interesting in that we were getting the percent ionization as a given. We were given the percent ionization, and we worked to solve for x. So that's a good one. Here I just throw in for fun 1 kb example and or 2 kb examples. So the first one, I have the general symbolism for a weak base is just the letter B. So I add that to H2O, so I get HB plus OH minus. So my Kb is HB plus times OH minus over B. And here's a example where the pH was given. This is given as 11.64. So I can get the pOH. I'm also given the original concentration 0.390 of B. So my pOH is going to be, let's see, 2.36. Does that work? 11 and 2 is 13. And 64 and 36 is another 1. Yeah, good. So that's pOH. I can get the H plus if I want, but that's not going to help me with this question. Let's find the Kb. So OH minus is 10 to the minus 2.36. So 2.36 minus inverse log to the base 10, 0.0044, or 4.4 by 10 to the minus 3. And lo and behold, that's what I have for my OH minus, 4.4 by 10 to the minus 3. My HB plus is also 4.4 by 10 to the minus 3. So then I get my equilibrium values. I lose 4.4 by 10 to the minus 3 and get Kb, which is 5.02 by 10 to the minus 5. Okay, if you really want, I can get the H plus, fine. H plus is 10 to the minus 11.64. So 11.64 was given in the question. 11.64 minus inverse log. 2.3 by 10 to the minus 12 molar. Okay, so that is an example of Kb. And then there's some questions that I'm going to assign for you to try on your own for practice. But that's good enough for now. And so look on EDSB to see what questions you're supposed to do. Sounds good.